So let's go over another sample problem. This is in addition to the sample problems that was presented in your module. So this is actually the elaborate part. So let us solve the elaborate part. So a soil element is shown in the figure. We are to determine the maximum and the minimum principal stresses, and at the same time, the normal and the shear stresses that are acting on plane AB. So first is using the equation that was presented in Unit 1 of Module 2. So we have here the two-dimensional soil element. First is we have to identify the given. So first given is the normal stress acting along x direction is positive 45. It is positive because it is compression. And then the normal stress acting on the y direction is also positive since it is compression, that is positive 85. Next is the shear. So we see that the shear stresses are moving away from the 90-degree vertex. So since it is moving away from the 90-degree vertex, this is positive. So taus of xy is positive 25 kilopascal. Solution. So first is we have to solve for the principal stresses. From Unit 1, we have learned that to determine the principal stresses, we can use the following equation. So sigma 1, sigma 3 is equal to sigma y plus sigma x divided by 2 plus or minus the square root of the quantity sigma y minus sigma x divided by 2, the quantity squared, plus taus of xy squared. So if we are solving the major principal stress, we use plus. If we are solving for the minor principal stress, we use subtract or minus. So since all the elements are known, we know the value of sigma y, we know the value of sigma x, we also know the value of taus of xy, we can directly substitute it. So since we are solving for the major principal stress, we use the positive. So that is sigma y is positive 85, sigma x is positive 45 divided by 2 plus the square root of sigma y is positive 85 minus sigma x is positive 45 divided by 2, the quantity squared, plus taus of xy is positive 25 squared. So this is 97.016 kilonewton per meter squared. Next is to solve for the minor principal stress or the sigma 3. This time, we will use the minus or the subtract operation. So 85 plus 45 divided by 2 minus the square root of 85 minus 45 divided by 2, the quantity squared, plus 25 squared. So this is 32.984 kilonewton per meter squared. Next is we have to solve the normal and the shear stresses on plane AB. So again, from our derivation from Unit 1, we know that the normal stress is equal to sigma y plus sigma x divided by 2 plus sigma y minus sigma x divided by 2 cosine 2 theta plus taus of xy sine of 2 theta. So since all the parameters are already given, we know the value of sigma y, sigma x, and the theta, which is 40 degrees, we can directly substitute it. So that becomes normal stress is equal to 85 plus 45 divided by 2 plus 85 minus 45 divided by 2 cosine 2 theta. Our theta is 40 degrees, so 2 times 40 is 80 plus 25, the value of our taus of xy, sine 2 theta, again 2 times 40 is 80. So our normal stress is equal to 93.093 kilonewton per meter squared. Next is to solve for the shear stress. So shear stress is equal to sigma y minus sigma x divided by 2 multiplied by sine 2 theta minus taus of xy cosine 2 theta. So shear stress, we substitute it, 85 minus 45 divided by 2, sine of 2 times 40, 80, minus 25, cosine of 2 theta, cosine of 80. So our shear stress is 15.355 kilonewton per meter squared. And then don't forget to place your summary. So we are able to arrive at the value of the principal stress, sigma 1, sigma 3, and then the normal and the shear stresses, sigma n and taus of n, with the use of the equations. So this is method A. Next, yes, we solve the same problem using the principles of Mohr's circle, and we see if we arrive at the same values. So same soil element. So from the procedures of the Mohr's circle, first thing is we have to identify the coordinates, but we also have to check the direction of the angle rotation. So from here, we see that the direction of the angle of rotation from the horizontal plane is clockwise. It is clockwise. So next is we have to identify point X and the point Y. Since we are identifying the coordinates, we have to identify point X and the point Y. So point X, this is our X point. So positive 45 because compression is positive. And then the direction of shear is clockwise also. Therefore, it is also positive. So point X has coordinates of positive 45 and positive 25. Next is point Y. This is our point Y. So again, point Y, positive 85 because it is compression, and then the direction of this shear is counterclockwise. Therefore, it is opposite the direction of the rotation angle, so this becomes negative. Therefore, point Y is positive 85 and negative 25. Next step is to plot the points on the Cartesian plane. So when we are plotting in the Cartesian plane, we see to it that everything is accurate, even the divisions, so that we will come up with an accurate answer, with an accurate reading as well. So we plot the points on the Cartesian plane. First is the point X, that is on the x-axis, that is 45, on the y-axis, that is 25. So on the x-axis is 45, and on the y-axis is positive 25. Next is we plot the point Y. So point Y is, that is 85 on the x-axis and negative 25 on the x-axis. So we have point X and point Y. Next is we connect the 2 points and then we draw the Mohr's circle. So since we already plotted the 2 points, let us connect the 2 points together with a straight line. And the intersection of the straight line to the normal stress axis, this now becomes the center of the circle. Then we draw the circle. And then from there, we can now identify the principal stresses. So we know that this is the maximum or the major principal stress. And we know that the intersection of the circle to the normal axis on this point, this is the minimum or the minor principal stress. So we simply do the reading. We read the value. So this is 97.016 and this is sigma 3 is 32.984. This one, I actually plotted this using AutoCAD. That's why I came up with 3 decimal points. But if we are plotting this manually, we are allowing up to 1 decimal point. If we are using the compass to really plot it, we can do the reading up to first decimal. So since I plotted this in the AutoCAD, I just got the 3 decimal points as well. So next is we are now to solve the normal stress and the shear stress that are acting on plane AB. So the next step is to measure the 2 theta, which is counterclockwise direction always from the reference plane. So the reference plane here is the horizontal plane. This is 40 degrees from the horizontal plane. So this is the plane which is the same as this one. So this is point Y. Remember, this is point X, this is point Y. So from our Mohr's circle, this is our point Y. Therefore, we know that this is our reference plane. So from this plane, we measure 2 theta with a counterclockwise direction. So our theta is 40 degrees. So we measure counterclockwise direction. That's 80 degrees. Next is we draw a line from the center of the circle towards the circumference. So from the center of the circle towards the circumference of the circle, uh, where the line intersects the circle, we now have a point here. So next is we project the coordinates of the point to get the value of the normal stress and the shear stress. So we project the point towards normal stress axis, and then we get the reading. So we read this one. So this is approximately 93, or more accurately 92.965. We also project the point towards the shear stress axis, and then we get the reading. This is 15.587. So there you go. You now have the value for your principal stresses, sigma 1, sigma 3, and then your normal and shear stresses, the normal stress and the shear stress. So don't forget to always place the summary. Place all the labels, but at the end, put also a summary. Next is, let's now apply pole method on the same problem. So again, pole method has the same procedure with the Morse circle except on the latter part. So we identify the coordinates, but first we check the angle of the rotation because this is our basis for the sign of the shear. So point X, this is our point X, this is our point Y. Point X is positive 45 because compression, and positive 25 for the shear because the direction is clockwise, and the angle rotation is clockwise also. Point Y is positive 85 and negative 25 because 85 is compression and 25 is counterclockwise direction, which is opposite the direction of the angle of rotation. So it's negative 25. Next is we plot the points on the Cartesian plane, point X and point Y. Medyo nauna lang yung point, pero of course, when you plot, mauna yung pag-plot ng itong mga line, di ba? You have to identify 85, and then 25, and then you put the point. And then next is we connect the 2 points together, and then the intersection of the line to the normal stress axis is the center of the circle, and then we draw the circle. So from there, we can identify the principal stresses, which is 97.016 and 32.984. And the next is we have to locate the pole since this is the pole method. So in locating the pole, we have to check the reference on the soil element. So again, this is point Y and this is point X. So point Y is horizontal line. So from point Y, we draw a horizontal line towards the circle. And then point X on the soil element is a vertical. So we draw a vertical line from point X to intersect the circle as well. So where the two lines intersect, that is your pole or P. And the next is to measure the angle from the reference plane. So the reference plane here is 40 degrees from the horizontal. So therefore, we will use this as our reference plane because this is also the horizontal line. So 40 degrees from horizontal line. And then from there, we connect point P, the pole, we connect the P towards the circumference considering the angle measured. So from pole until to a point where it intersects the circle. And then, of course, this point will have its coordinate. So to get the coordinate of this point, we project it first to the normal stress axis and then we get the reading. This now becomes your normal stress, which is 93.055 kPa. And we project it also towards the shear stress. We get the reading. This is 15.424 kPa. And then don't forget the summary. So observe that if you're going to compare the results, so we had solve the same problem using method 1 by equation. This was actually discussed in module 2, unit 1. And then method 2 is by Mohr's circle. This is unit 2 in your module 2. And then method 3 is by pole method. This is unit 3 in your module 2. So observe that the results for the principal stresses are almost equal. Same with the normal and the shear stresses. They are almost equal. So 92.9, or if this is rounded up, this is also 93. And this is 93.05. So there is a very minimal or less difference between the answers, but basically they are almost equal. So by equation, by Mohr's circle, and by pull method. So this is module 2.